different substances and then compare them in calculation. 53. So the graph is important, and on the side I've provided the transition process, which you can actually just write here. So basically these, so for example, from A to B, as the temperature increases, internal energy increases, and this is due to the increasing kinetic energy of the particles only. Potential energy remains constant since there's no change in state or spacing. So therefore, potential energy change when so A to B, B to C, repeat okay. And the other thing that you need to understand is that at a given temperature, you can have both solid and liquid. It depends on which part of the process are you observing the heating, right? So if you're starting at the start, then it's solid. At the end, it's liquid, but the temperature is constant throughout. Okay. It's outside.
So when this is the same
February. Are you guys done? So basically notes of what we did last class. So I will show you an experiment, and then this topic is over. Thermal physics. The next topic is called ideal gases. So we can start over. How to plan it? Yeah, so there are 8 questions you need to answer. First is what is the independent variable? Then what is the dependent variable? What's the control variable? This is the first thing you need to find out. If you can't figure that out, then you can't really do the experiment. So first independent, dependent, and control. And once you figure that out, you need to write down how to find the independent, dependent, and how to keep the control constant. So like what apparatus would you take? How do you take your measurements? So that's the next part. Then using that data, the most important part, I think around 7 marks are in that part, how to find the quantities you're looking for. So you find in every planet, they'll say, show that the constant K is a constant, or find the gradient, or show this relationship is valid. And they'll give you usually a very complicated equation. If you look at the equations, they're not straightforward. Like a lot of variables, powers, and everything, right? So what you need to do there is you need to rearrange that equation to form a straight line. And for that, you need to learn, or you need to know this particular thing in math called linear log, where you take a logarithm on either side and you can convert any equation into a straight line. And then you write how do you find the constant from the graph. And then at the end, there's like a precaution or an improvement for 1 or 2 marks. That's usually the standard. So independent, dependent, control, how you find it and how you analyze them. That, you know, what kind of graph do you plot, how do you find the gradient, and 1 precaution and 1 improvement. That's the process. Now, there's no way to study for this. And the reason behind that is there's no syllabus for your plan. They can ask you literally anything. Of course, it's supposed to be based on your A2 syllabus, right? But they ask you things that are not from AS or A2, just random experiment, right? So the skill that you need to build here is how to plan the experiment, not learn a particular experiment and expect that to show up. Now, things that you can learn here is, for example, how to measure the strength of magnetism. That is something that you have to learn beforehand because you can't figure that out in the exam, right? So you should focus on how to take measurements of different quantities out there. And then I feel like so your school is doing paper 5 at the start. It's a little difficult because there are a lot of things you haven't learned yet. For example, do you know what a Hall probe is? Yeah, but the thing is, paper 5 relies a lot on Hall probe and calibration of Hall probe. So Hall probe is something you learn in magnetism, and you learn how to build a Hall probe. Hall probe measures magnetic field strength, right? So you can't just use a Hall probe. You have to calibrate it. You have to make it. You have to fix it, and then you can use it. So that process has to be mentioned in paper 5 paper. So those are things that makes it appropriate to do it after those chapters. So I think after magnetism is the best step, because after magnetism, the chapters we have, those are too technical and they can't have any experiments from it, like medical physics, astrophysics, right? So magnetism is the borderline. Once you finish magnetism, you should be able to do any planning out there. Either base 10 or base C. So it could be natural logarithm or log. But if there is E in your equation, then it's better to take natural logarithm, because natural logarithm E is 1. So you can cancel that out. So if there is an E function in your equation, it's best to take natural logarithm. Yeah, you can do that as well. Generally, that doesn't work, but there are places it works. Okay, let's continue. So just a quick reminder of what this is. Last class, I showed you the process where you have a solid and you heat the solid. This is called the heating graph. Okay, this the name of this graph is called the heating graph. Oh, naam de refer karna, but for our reference, we'll call it the heating graph. So the heating graph is the graph that you obtain when you heat a material. And turns out the graph when you heat a material is always the same. Whatever material you have, when you heat it always takes this journey. So what's the journey? It starts at a low temperature, and as you heat it, the temperature keeps increasing gradually like that, and it increases at a constant rate, and then it reaches a point. And at a particular temperature, you'll notice that you're still providing the heat. You're continuously providing the heat, but you'll notice that the temperature remains constant and there's no change in temperature. And then suddenly, again, the temperature starts to rise. So then the question remains that you're still providing energy. Where did the energy go? And a simple answer to that is that the energy was used to break or weaken the bonds in your solid so that the solid could turn itself into a liquid. Now, you have to understand this is a gradual process. As a transient process, time change. So at the start of your process, you'll probably have 100% solid, right? As the thing progresses over time, it starts to melt, and at the end of the line, you'll have 100% liquid, right? So if they say you stop at halfway here, right? So you have to do your math taking 50% solid and 50% liquid. So these are complexities they'll add to your question, okay? And once you reach this point and you increase your temperature, you'll notice the temperature rises once again, right? And then again, the same thing happens. So this state change that you see here is from solid to liquid. This change that you see here is from liquid to gas. And the gradient of the graph that you see here, I'm going to correlate in experiment Corbo, is actually based on your specific heat capacity. The higher your specific capacity, the lower your gradient, okay? Because high specific heat capacity means you need more energy to raise the temperature. So therefore, the rise in temperature will be slow. So it takes effort for the temperature to rise. So yeah, the idea is that whenever you have a low specific heat capacity, temperature rise will happen rapidly. High specific capacity, temperature rises slowly, okay? And yeah, that's about it. Just একটা part বাকি আছে এই জিনিসটা আমি এখন ডিসকাস করব, বা তার সাথে যদি কোনো প্রবলেম আছে বলতে পারো. As you can see, there's an increase in temperature here. It means there must be what increase here? K. But you can notice there's no change in temperature here, so the increase must be P, potential energy. But one very important thing, throughout the whole process, right? Starting from here, there, everywhere, what is definitely increasing? Internal energy, okay? So internal energy into part the same. So there's always an increase in internal energy here. So anyways, this is the heating graph that we have. And এখন যে জিনিসটা একটু ডিসকাস করতে চাই ওটা হচ্ছে এটা, and I talked about this last class. See if you can answer this or not. So these are questions that you should anticipate in your paper, which is when you heat something, the graph for water, for example, looks something like this. It goes from here, minus 20 degrees Celsius to 0, right? And then it melts very rapidly, and then it goes up like that. And then this part of the graph, and I mentioned this last class, is something like this actually. So the boiling point, right, requires a lot of effort. So if you see the time comparison, right, for melting, you had that much time taken, but to boil the liquid, the time taken is, drastically higher, right? So the question is, why is the time taken for boiling so much longer? So, so the question is, why does boiling? Someone's still there. Why does boiling take exponentially longer? Huh? But I mean, to like any question drastically longer. So yeah, why does boiling take drastically longer, right? So I'm actually need to clarify for you. So the problem that students have with this question is that they think that solid particles will erokom dikhte. So they're very closely packed, right? Liquid, what would the particles look like? Same. The liquid particles are actually, they look exactly the same, with one difference that the liquid particles can what? Move around, right? They can like shift their position. And once you go from liquid to gas, the particles become very far apart, right? So this is liquid, and how the gas particles look like here. So extremely far apart, let's say like that, okay? So the question is that why is the energy taken for this transition, right, so much small compared to the energy taken for that transition? And if your answer is that it is because solid particles and liquid particle is not much change, liquid to gas is a very large change, right? You can see the structure here. I don't know if you remember O level say এটা ছিল যে solid particles গুলো এরকম দেখতে, মানে if I draw them, liquid এ কিরকম দেখতে, same, liquid এর particles গুলো একদম same দেখতে থাকবে। একটা difference হবে যে liquid এ there's a particle or a couple of particles that can what move around, that's why they can slip and slide over each other, right? But then if you go to gases, the particles are so far apart that my screen is not enough to show their spacing. So do you see this particle here and that particle there, right? That is considered to be close in terms of gas spacing. So gas spacing is even further away, okay? So the question is that if you think that's the reason, তাহলে এনার্জিটা কিন্তু একটু খাওয়ার কথা ছিল, মানে the time taken should have been that much, somewhere here. My question is, what we are seeing here is awfully longer, because if we had taken into account the fact that they go very far apart, অনেক দূরে সরে যাচ্ছে, right? তাহলে কিন্তু টাইমটা এরকম আসার কথা ছিল, মানে this is the time that should have been, right? But do you see that the time actually taken is much more longer? So there must be something else that's playing a big role here. So I'll repeat my question one more time. When you go from solid to liquid, the time taken is t, because the spacing is so large. Gas is a liquid থেকে gas with a time নেওয়ার কথা ছিল 2t, let's say, but turns out the time taken is like 7t, extremely large time taken. So the question is that why is it so drastically different? Right, and that will result in that much. So why is that extra part there? And that will account for this amount of energy. That's it. I mean, the spacing part that you guys are talking about, right? It's this part. So that maximum spacing that we are discussing should take this much time, right? Compared to that. But what is that extra time for? It is because going from liquid gas, a lot of energy, heat, a lot of energy, it's taking longer. But why is there this extra part there? It's an actual exam question, and I hope that tomorrow parba. And usually it's there's someone who figures it out. I can give you hints, but একটা hint পারি আমি, ওই hint দিলে answer চলে আসে, so আমি ওটা দিতে যাচ্ছি না, okay? No. তোমরা questionটা বুঝছো? Because when I want to answer, I hope that you understand what I'm trying to answer, okay? Is it because the gases require more energy to overcome intermolecular forces? Yes, and that accounts for that much energy extra. So what's that extra part here for? আচ্ছা আমি বলি কি হচ্ছে। No, you guys are just in random words now. আমি বলি কি হচ্ছে এখানে, এটা একটু realistic যদি point of view থেকে দেখো, you'll understand what actually is happening. So you have a container here and you have water inside this, right? And you want to boil the water, right? So what you do is you start boiling the water, and the water here will turn into gas. And what will the gas do? Escape, right? So the hint that I have is that water boils at 70 degrees Celsius on top of Mount Everest. So if you go to top of Mount Everest, water boils at 70 degrees Celsius. If you go to the edge of our atmosphere, exosphere, right, water boils at 10 degrees Celsius. So if you have a cup of water at 10 degrees Celsius, you have gas, like you say. In outer space, water boils at -4 degrees Celsius. So it's supposed to be solid at -4, right? But can boil it. So that is the hint, right? So what is actually happening here? So what's actually happening here? Yes. Okay. So pressure. How does pressure have a role to play here? Why is pressure affecting the energy taken? Okay, close. So what's happening here is at sea level, where we are right now, it might not appear to you because we are born into this, so we have no idea how it is supposed to be, but there's extremely high pressure around you, 101 kilopascal. That's a very large pressure. It's called a what pressure? Atmospheric pressure. And we're designed to be in that particular pressure. That's why if humans go to higher altitude, you start to suffer. You have altitude sickness, nosebleed, you start to feel dizzy, right? Cannot, because the pressure is low out there. So the thing is, we don't experience this, but there's actually a lot of air around you. So when this water turns into gas, it has to move into the air here. And the air doesn't want things to move into it. So what does the gas need to do? Push the air out. So you can just steamটা বের হচ্ছে, the steam actually has to push the air out of the way in order to move out. And in order to push the air of the surrounding outwards, what does your water need to do? Work. And that extra energy that you're seeing here, that's this part of the graph, it's actually the energy needed to do work against atmosphere. So atmosphere ke push out করার জন্য, this is the extra energy needed. So if you perform this experiment, right, in a vacuum, you'd find this is the answer. Just that much. The actual amount of energy needed to weaken the bonds, right? Which is actually not that much. But if you do this in atmosphere, where there's actually gases around you, and you need to push the gases out, right? The amount of work done is very large, and that's why it takes much, much higher. So in last class of Boltzmann, when you try to boil water and completely, boil the water out from your pan, it takes a lot of time. Compared to, let's say, you want to melt an ice, right? But tabular so before you even try, it's melting, right? Because of the atmosphere and the temperature around it. It's a very easy process. But when you want to go from liquid to gas, it's very difficult because the water has to push everything out, and that requires a lot of work to be done. Okay, so yeah, this is like a question that we get. So from now onwards, when you talk about melting point, boiling point, especially boiling point, you have to take into account what here? The pressure of the surroundings. Okay, melting is a problem. Why not just boiling a problem? Right, it answered the data. The process. If you have questions, let me know. I can clarify. Experiment. So your paper 4 has experiments in them. Key experiments I'm going to explain right now. I think we haven't done any experiments yet, so this is the first one we'll be doing. Right, so that's all you need to know about the heating curve. Any questions, you can let me know. I'll just go to this answer here. So energy needed for X to Y is drastically greater than from P to QY. Energy needed to separate the bonds and gases is much higher due to the large spacing, which you guys have acknowledged. And also due to the work done against the atmosphere, overall requirement is exponentially higher. Okay, so there are two factors out there. Yes, it's true that spacing is beshi lagbe, but data lagteche it's even way more than that. And there are two factors that account for it. Okay. Right, so do you get experiments in your paper 4 papers? So you do. And what experiments do you have out there? In total, there are 12 set experiments. 12 mane hocche protekta chapter theke from now onwards, you'll find one experiment that they'll just ask. They'll just say, do the experiment. They'll give you a page of blank space, 4 marks, 6 marks, 8 marks. Okay, variations. Okay, সবচেয়ে বেশি experiment আসে from magnetism. So magnetism, we have something called a velocity selector. It's a device that helps you select velocities of particles. We have in magnetism something called a Hall probe. So we Hall probe to design correct experiment. You have Lenz's law demonstration for 5 marks, right? So these are experiments that they'll give you in your paper 4. These are not designing. They're not planning. We already know about them. You just have to recall them. Then there's something called the Millikan's oil drop experiment. It is from your charge chapter. It's basically oil drop is full of float for it. You can stop them, and by making them stop, you can find out what the charge is of particles. Okay, so these are experiments that we have. This one is a very good experiment because we'll introduce ideas here that are technically very challenging, and I'm surprised that A2 they were already introduced course, but okay, it's a good thing that they have done, but it's too challenging. It says specific heat capacity for and latent heat of fusion mode. You need to find the specific capacity of an aluminum block, and the other experiment is to find the latent heat of fusion of water. Experiment. Okay, aluminum block that they start with because you had in your O levels. Do you remember an aluminum block finding the specific capacity? So can anyone run me through the setup? What does the setup look like for finding the specific capacity of an aluminum block. Because if you remember, you couldn't just find it normally. And I don't want to go through the whole process again because O levels is kora chilo eta, but I just want to see if anyone remembers. So here's your aluminum block. Bolo ami ki korbo? Yes, very good. So what you need to do is you take your aluminum block, right? And you create cavities in them. Cavities or holes in them. Why? What's wrong in keeping your temperature probe outside? Heat loss. Achha, okay. So those who don't know, I don't know if you have, if you recall it, it's almost 2 years now. O levels is chilo experiment. Our weekend chilo, you're given an aluminum block like this, right? And they want you to find the specific heat capacity of this block. So first thing, a type of experiment you need to do something is figure out what do you need to find. So what's the formula for specific heat capacity? Yeah, del Q equals to MC del T. And I need to find C. So C is supposed to be what? Del Q divided by M del T. Now, how do I find the energy that I'm providing to this particular block? Do you remember? Ki use kara hoto? Like, how do you find the heat provided here? Because if I take a flame here and put the block on a flame like that, do you think the block will heat up? Of course. But can you find how much energy the flame is providing to the block? No. Okay, because the way the flame works, it's very random. And you can do something from chemistry, but it doesn't work here. Do you know a calorimeter? The specific capacity how much energy was lost in the burning of the fuel, right? Because not all the energy of the flame goes where? To the block, right? So therefore, it's not a very efficient method. So is there a better way of doing this? Yes. So Amra jeta korbo will provide electricity. So the heat you're providing here is based on the assumption that we are providing heat energy here, and that heat energy is provided by what energy in the heater? Electrical. So we are assuming that the electrical energy of my heater will be converted to what energy of my block? Yeah, the thermal energy, right? So that's what I'll use here. Somewhere I can chalo mass jante hobe, change in temperature jante hobe. And for the heater, what I'll do is I'll make a cavity here. I'll make a small cavity there as well. And we'll place what into the cavity. One of them will have what inside them? Your heater. So draw kore diye jinishta too. So the setup goes something like this. You make two cavities, and one of the cavity will contain the heater, and the other cavity will contain your thermometer. Okay, so these are two holes in your block. Do you follow so far, Kyoche? And then what you do is in one of the cavities, you'll place your heater. There's a name for this heater. Do you know what that is? A heater erokom dekhte hoy. So there are two wires like that, and at the bottom you have like a very big coil. Do you know what these heaters are called? Erokom. Yeah, what was it? There's a name for this heater. No. Immersion heater, right? So there's a coil that you immerse into whatever you want to heat, and as you immerse it into whatever you're trying to heat, you can find the temperature, right? Or provide heat based on how much electricity you're providing. Okay, so that's the immersion heater. And on the other side, what do you provide? Thermometer. So on this side, you have your thermometer. So exam diagram draw korba, eta draw korba na. Acha, eta just buchhano jo dekhachhi. The diagram that you draw is much more easier. So what do we do here? We add something else. Do you remember what do you add here? Yes. Where do you place the oil? Why? No. Exactly. So these are cavities, these are holes, right? So if you place your heater in a hole, is there direct contact between the heater and the wall? No, right? So to improve conduction, what do? Is you fill this cavity with what inside? A conducting oil. Sometimes students will complain that what if the oil ruins with my experiment, right? It shouldn't, because the amount of oil that you're placing here should be negligible compared to the amount of aluminium out there. You also provide oil here. Oilটার purpose main একটাই কাজ, to improve what between your heater and the surrounding conduction. So the heat from the heater can easily transfer to the block now because yes, so we use a conducting oil. Conducting oil means its purpose is that it's a very low specific capacity and it almost instantly heats up. Okay, so yeah, this is the heat transferred here, and then the heat will then go into this part, and then finally, what would my thermometer give me? The rise in temperature, right? So this is the setup that you see. Setup. Okay, so this is my experimental setup. I'll label and everything, but the thing that you need to know is what should my equation here be? So in the equation, in place of Q, I need to provide electrical energy, right? What's the formula for electrical energy? VIT. তোমাদের syllabus তো allow করে না, মানে ওরা ওটাকে avoid করে. They do something easier. You just find the watt of this heater power and use power into time. Okay, not VI. So I'm just taking a separate apparatus use for what is that? The stopwatch, because I need to know the watt for my heater, the time it is on. And time record is important. We'll see soon. Okay, so this is connected to your heater or power supply. So this is where the power comes from. You have your immersion heater here. This will provide you with the heat. A experiment that তোমরা বুঝবা যে how technical can an experiment get. Okay, I'm just so far just doing what we had in our O levels, and now you will see A levels are key at for it. Thermometer. What do you have in these gaps? Oil. Okay, so conducting oil, and this is your what block? Aluminum block. And stopwatch. So that's the setup. এখন আমরা হচ্ছে we'll try to find the specific capacity. So what do I do here? I will just use this equation here. This is going to be power into time and divided by M into change in temperature. So what are the quantities that I need to record here? I need to find your power. I need to find the time. I need to find the mass. I need to find the change in temperature. And once I do that, now listen carefully. This is the A-level part. Once I do that, I will get a value for C, obviously, right? And it is going to be very far from what it should be. That's what happens. Okay, so if you do this experiment in lab, you'll find that the specific capacity that you get here is almost 30 to 40% wrong. When it's supposed to be 700, right? In a lab, answer 600, sometimes or like 800. But it's like 40% off. So the question is, what do you think would the value for C in practice be? If you have a flawed experiment, right? Should the value for specific capacity be higher than what you anticipate, or should it be lower than what you anticipate? A question to So I do this experiment, I get a value for C, right? And my experiment is flawed. And the flaw is very obvious. I don't think I need to spell it out for you, but you know what the flaw is. Key flaw. Heat loss. Heat loss to the surrounding. The block is losing heat to the surrounding, and it's giving itself some heat. So heat loss যদি account না করো তাহলে যেটা হবে you will have a bad answer, right? And my question is, if there is heat loss actually taking place, how does that affect the value of C? It's going to be lower. Okay, does everyone agree, or should it be higher? It should be higher. Okay, and why should it be higher? Let me explain it to you. So C with heat loss, okay, with heat loss, see what happens. C equals to P into T, power into time, divided by M del T, right? So del T is the change in temperature. Let's assume I'm providing the same power, so power constant. I'm providing the same time was same, for the same mass. Do you think with heat loss, would my rise in temperature be less than anticipated or more than anticipated? With heat loss, less, right? So that means this is going to be lower at the value than anticipated. And if this is a lower value than what you expect, shouldn't C be higher than what it should be? So it's supposed to be a higher value, okay? There's another alternate version. Some students prefer that, which is C equals to power into time divided by m del t. এখানে power constant, mass constant, and for the same temperature change, would you require more time in reality or less time? More time, because it's going to take more time because there's energy loss. So if your time taken is more, what should the value of C again be? Higher. So just understand that whenever there's heat loss taking place, the value for C or specific capacity is generally going to be more. আমাদের thing হচ্ছে O levels we're okay with that. If you remember, heat loss হয়, answer আসে না, শেষ, right? A levels they're not okay with that. They want you to get the exact value for specific capacity, like the actual value. So you might be wondering that how did somebody find the actual value? Did the heat loss সবসময় হয়? We're gonna learn that, okay? So ওইটা start করতেছি in a minute. But something else that I want you to learn or know is that we don't do experiments like this where you take one time, one power, one mass, one temperature change and find C. What do we do? Like for experimentation, right? So when the planning it and notice for any experiment out there, you don't find a value and conclude that as the answer. You do something. What is it? Repeat an average, yes. Arkichu. There are a couple of quantities that means that we need to approach our experiment in a particular way. কি করবো আমরা কি একটা mass নিব, একটা time নিব, একটা temperature change, একটা power দিয়ে answer বের করবো, নাকি average যদি বের করি আমি একই জিনিস 3-4 বার করে average বের করবো, নাকি is there something else? Yes, we go for graphs. So just always remember that when it comes to experimentation, যেভাবে possible হয়, try to go for a graph. And this is actually a very good experiment to have a graph. Why? What is change in over time? তাহলে টাইমের সাথে আমি যদি হচ্ছে আরেকটা ভেরিয়েবল নেই, then I should have a graph, right? So I'll plot my graph like this, where my x-axis is going to be time, and the y-axis is going to be change in temperature. Okay, so I'll use change in temperature because that's the other variable. Can you tell me what does the gradient of this graph give me? What does the gradient of this graph give me? Should it be a curve? Should it be a straight line? And if it is whatever it is, what should the gradient of the graph provide me? And why are graphs better than repeats? It helps you find anomalies, which you wouldn't know by repeats. So sometimes it could be all 3 repeats are wrong, and that means the system has what error? Yeah, so the graphs are very project. Yes. Okay, so that would give me a very C is equal to P into T divided by M del T. Gradient amar jodi ekhane graph ashe, shouldn't it be del T by small like time, right? So if I make that my subject, del T by T, and if I flip it over, what should that be? It should be power divided by MC, right? So that means I should get a straight line. Why should I get a straight line? Power, it's a constant. Mass, it's a constant. C, it's a constant, right? So your graph should be a what line? Straight line. And এরকম দেখতে আসবে. Now, এটা হচ্ছে একটু আগে আমরা করে আসছি. Do you remember the heating graph had same axis? The one that we just finished, the heating graph. Wasn't it time and temperature on the y-axis? And remember, I told you that water has a graph with a lower gradient because specific capacity is what? Higher, right? So specific capacity বেশি হয়, wouldn't the gradient be lower? So the higher your specific capacity, the steepness of the graph falls. And if this was a very good conductor, your graph would be very steep. And that's common sense. Why? In a very short amount of time, the temperature rises very rapidly. Isn't that a trademark of something that's a good conductor, right? So anyways, this is my graph. The gradient of the graph will give me my specific heat capacity. And that will also be a wrong value. Okay, and so I'm both kind of wrong with theta. So gradient. So যা করতেছি আমরা এগুলো কিন্তু more or less O level standard still. Maybe this particular graph gradient বের করাটা I might say could be AS standard. A2 তে কি করতে হবে দেখি. So yeah, so far, do you have any questions before I get to the technical part? So এখানে কি কোনো confusion আছে না? Yeah, so C specific capacity is power into time divided by mass into change in temperature. My y-axis is change in temperature and the x-axis is time, right? So if I divide this by this, I should get, by rearranging my equation, P by MC. And let's say I'm doing my experiment, I want to find the value of specific capacity. What will I do? I'll find the gradient, right? And I know power, I know mass, I can find the value for C. Okay, so I'll just keep this here. Also, যারা planning experiment করো একটা জিনিস মনে করে যদি বলে যে how would you find C, some students will just stop there. এটা ওরা allow করে না, কি করতে হবে? C কে subject বানাবা, subject বানায় you have to write down what you do. So power divided by what? Mass into gradient. এভাবে লিখতে হয়. So you'll find in a mark scheme in every place that they write it this way. You have to write it this way. Like you have to acknowledge what the value is by making it the subject. Okay, so now questions for you. এখন তোমরা হচ্ছে try করবা to solve the problem here. So the question is, by doing this experiment, and listen carefully, it's like A-level at the topic. By doing this experiment, we tried to find the value of C, and the C value is higher than expected. So এটা হওয়ার কথা ছিল 700, 950 আসে, which is very off, right? And then that's not good enough. How can I get the actual value? So the main culprit in this whole process is what? Heat loss to the surrounding, right? So yeah, I can reduce that. You know how to prevent heat loss and reduce heat loss. So first question, how do you prevent heat loss? Vacuum, but vacuum will cause radiation, right? So how do you prevent heat loss? Insulator. Anyone else? How to prevent heat loss? Yes, thank you. You can't prevent heat loss. The Nobel Prize waiting for you. How do you prevent heat loss? Heat loss is inevitable. It will be lost. You can what heat loss? Reduce it. Okay, so the answer and we prevent heat loss by just putting like wool on it, right? It doesn't work that way. Okay, so you can reduce it. Reduce করার জন্য যেটা করতে পারো, you can wrap this with an insulation, right? So এই পুরো জিনিসটাকে you can cover with wool or something that will minimize what? Radiation and conduction, and also stop what process? Convection. Do you remember the working of fur from biology, how it works? It traps the air, right? Or wool, they traps the heat inside. So yeah, that would be a good start. But যদি বললাম না তোমার অ্যান্সার হওয়ার কথা ছিল 700 আর 950 আসছে, এই জিনিসটা প্রোভাইড করে এটাকে আমরা বলি ল্যাগিং। এই ল্যাগিং প্রোভাইড করে you can bring it to 900. It's still very far from 700, right? So how do I get the actual value? How can I actually get rid of heat loss entirely? Because যতক্ষণ যাবে না ততক্ষণ C value the right আসবে না, right? So how do I do this? No, there could be, but the problem is that shape and size of your block can be different, right? And the factor would be then different for different blocks. So তোমার কি question বুঝছো? আমার questionটা হচ্ছে that I want to find my value for C without having heat loss as a factor that affects my answer. So how do I get rid of heat loss? And now we just mentioned earlier heat loss বাদ দেওয়া possible না. So কেমনে correct answer বের করব? Lower value of mass. Acha, that's actually not bad, but as an A student, you should be able to answer why we should do that. Why a small mass that leads to a small rise in temperature in a very short time is a recipe for disaster. Yeah, it will result in massive uncertainty. Remember, small values, right? So তোমার uncertainty অনেক বেড়ে যাবে। তখন দেখা যাবে যে you have error plus a lot of uncertainty. It's something else, right? So what can we do? So if you have exhausted your ideas, then I'll teach you what the proper way is. But our current share itself, we want to clarify the সবগুলো cover হয়েছে. So lagging day হবে না, small mass day হতে পারে, but it's going to be less likely to give you an accurate answer because of uncertainty. But there's this one answer that অনেকে বলে, তোমরা কি বলতেছো না? There are two answers, by the way. একটা হচ্ছে অনেকে পারে, আর একটা খুবই টেকনিক্যাল, ওটা আমি শেখাবো. So what would be the other way? Unfortunately, no. So otherwise we could have subtracted it, right? আচ্ছা আমি বলি, এটা এই বছরই O levels a couple of students said it, so I think they have seen it somewhere. So let me explain what this is. It's called a pre-chilled block. What does it mean? So you take the block and you put it in a freezer first, and you cool it down to a very low temperature. Because you have to understand, heat loss will only take place if your block is what than the surrounding, warmer, right? What if I bring my block down to like a lower temperature? It's not going to lose energy. But then the question is, it'll gain energy, right? So how do you fix that? So there's this very ingenious way of working around it. So what we do is we take our block and we cool it down to minus 20 degrees Celsius. And we heat the block from minus 20 degrees Celsius to 20 degrees Celsius, which means that from the first part of the, 20, no, 40. So for the first part of your heating process, isn't the block cooler than the room temperature? Room temperature is 20, right? So minus 20, minus 10, 0, 10, 15, 20. Aren't these all temperatures when your block is gaining energy, right? And then you take it from 20 to 40. Wouldn't that be the part where your block is losing energy? And if you have done, and it's a linear process, so if you have done a process where it gained energy from the atmosphere, and then it lost energy to the atmosphere, and that energy loss and gain is based on temperature difference, shouldn't the amount gain and loss be equal? So the effect becomes what? Cancels out, okay? So the best way to do this experiment, the easy way out, is that you start the block with a very low temperature so that there's a part of the process where it gains energy from the atmosphere, and there's a part of the process where it loses energy to the atmosphere. We try to make sure it's for the same duration. What would that ensure? The amount of gain and loss is what? Equal, okay? That's one way of doing it. But the one I want to teach you right now, এটা is brilliant একটা idea, whoever came up with it. Look at this, okay? কি করে ওরা? So I mean, next class আবার বুঝাবো, আজকে just to তোমাদেরকে start the day. So এই processটা you can use for any thermal physics experiment, okay? এটা খালি এটার জন্য না। And তোমাদের syllabus so far হচ্ছে ওরা অন্য জায়গায় জিজ্ঞেস করছে, এই particular experiment করে নাই। So this is my experiment, right? Listen carefully, it's technical. What I'll do is I'll set my power rating of the heater to P1, and I will take a stopwatch and record the time here for a duration of T1. And because of that, my temperature rise will be del T1. So if I want to find specific capacity, what would my formula be? So power into time should be equal to energy gain, which is what? MC del T1. Do you agree? But we'll put a plus here and we'll write something here called phi1. What is phi1? Energy losses around it, right? Because I mean, reality all the power or the energy you provide, right? Isn't it going to the block and the surrounding? Do we know the value of that? No. I'm on the phi1 কোনো idea নাই, okay? I know this, I know that, I know all of these, but I do not know that. So the thing is, এটা তো বের করতে হবে আমাদের, okay? This is the unknown. তোমরা কি বুঝছো what this equation is? So this is the amount of energy you provided. The energy went to the block and there was a loss out there. I don't know the value of loss, right? Okay, fine. Let's just assume the loss is 1500 joules. We do not know this, but I'm giving you a number just to keep in your mind. Next, what you need to do is repeat this experiment with the power of P2 for the same time. And the temperature change in that case would be del T2. Do you agree? So what should my equation be here? P2 into T1 equals to MC del T2 plus, again, heat loss of it. Let's call this heat loss phi2, okay? Phi2 টা কি তোমার মনে হয় সেম হবে না একটু বেশি হবে যদি আমার পাওয়ার বাড়াই দেই? বেশি হবে, right? So let's say this value here is 1550 joules. Then what we do is, and this is done in experimental physics very often, we find the difference. And when you find the difference here, you'll find what here? এটা একটা থেকে আরেকটা যদি minus করি, what will it be? P1, actually উল্টাটা হওয়ার দরকার, মানে নিচেরটা থেকে উপরেরটা, but ধরো করি এটা। So P2 T1 minus P1 T1 equals to কি হবে? MC del T2 minus del T1 plus এটা কি হবে? Phi2 minus phi1. Are you with me so far? So I'm খালি কিন্তু এটা থেকে এটা minus করলাম. Now you'll notice something. আমরা P2 জানি, T1 জানি, P1 জানি, T1 জানি, M জানি, এটা জানি, এটা জানি, এটা just হচ্ছে আমার বের করতে হবে। আর এগুলা জানি না আমরা। We make a very bold assumption here. We assume phi1 is same as what? Phi2, and we cancel them out. And by doing so, we actually find the answer 700 volts, 701, 702 এরকম আসে। How is it justifiable? It is justifiable because when you just do one experiment, what is the impact of the energy loss on your answer? 1500 joules. Do you agree? But when you take difference in both of them, what is the overall impact? just 50 joules. কারণ এই যে এটা minus এটা করলে what is the value here? 50 না? Isn't 50 way less compared to 1500 joules? So তখন আমরা experiment করে দেখি is actually very negligible, the difference. And eventually, we don't know what the actual value of heat loss is, but by finding the difference in these two, we can actually cancel out these values. And it does give us a very accurate value for C. And this can be done for any experiment where you don't know what the heat loss is. What do? You do the experiment with one power setting, and you repeat the experiment with a new power setting, and then you find the differences. While finding differences, we assume that the heat loss values are so similar that they what each other, cancel each other out. And there, as a result, what's the impact on your value? Nothing. Okay, so এখানে 1500 এ যদি আমি খালি এই ম্যাথটা যদি করতাম, let's say, wouldn't my C be based on an error of 1500 joules? If I just did this experiment on its own, wouldn't the C be based on an error of 1550 joules? But if I did this, and found the difference, you can see mathematically, you take into cancel out with it, or cancel out now. What is the overall difference going to be now? Just 50. Isn't that very negligible compared to what the actual values were? And yes, this is a technique that's used in experimentation to improve your accuracy. And what are we trying to like mitigate or negate from our answer here? Heat loss by canceling the two unknowns. So yeah, this is a technique that's used. I'll give you a note on this thing, but to make the basic idea, right? So this is what we have in our A levels, A experiment again. Utilize. So next class, I'll explain this one more time, preferably with numbers. Phi is heat loss. Quantum physics. So we'll only have 2 chapters left, which is it's at the front. There's like a rack there, the big one.